Good morning. We're going to keep talking about what we were discussing yesterday. The most important thing that we addressed, and I hope that made that point very clear, was these light cones. So this region of space-time, which is enclosed by slopes of each regarding to the say y-axis, the t, so the time axis of 45 degrees. Okay, so if you want to be causal, if you want the speed of any event to be less than the speed of light, that event must live within that cone. Okay, so 45 plus 45, 90 degrees of aperture on the future, and the same in the past. Okay, anything which has happened to you in your life in the past and it has been causal must have been contained in that 90 degrees cone. Now we looked into flat space-time, and today we're going to move to the vacuum solution by Schwarzschild. So we're going to look into Schwarzschild space-time, so that we have zero terms. If you look at the answer equations, we have on the right terms we have zeros, and we're going to assume perfect spherical symmetry. We will see that, I'm going to draw it right now, but we're going to see that the kind of conformal diagram that you have is very similar when you are far away from the black hole. And that should be kind of intuitive, right? Because I discussed that in the last few minutes of the last lecture, I think. When you are very far away from the black hole, even if the black hole is supermassive, which is something very fashionable these days, and you find supermassive black holes in every Hollywood movie, even if it's supermassive, from the point of view of the galaxy, it's microscopic. It's something irrelevant, something that in principle should not matter at all. Nevertheless, and this is important to know, we found that there are correlations between that supermassive black hole, which is microscopic. Think of, for instance, a black hole with a mass of 10 to the 6 solar masses. The Schwarzschild radius, if you want the radius of the black hole, something that we usually employ to give the black hole some size, has a length of about 10 to the minus 7 parsecs, if I am not wrong. I just making it, calculating it off the top of my head right now. I think so. So 10 to the minus 7 parsecs. Remember, a parsec is of about 3.3 light years. Okay. And the size of a galaxy is of a few thousands of parsecs in diameter. For instance, the Milky Way, or if you want our distance to the galactic center, where this supermassive black hole in principle is lurking, is of about 8 kiloparsecs, so 8,000 parsecs. So how on earth could something as tiny in size as 10 to the minus 7 parsecs have an impact on the formation and evolution of a structure as large as, say, 15, 16 kiloparsecs, thousands of parsecs? Well, we don't know, but the point is that it looks like there is something going on there. It looks like this tiny object knows about the evolution of the host galaxy, or maybe I should say, and the galaxy knows about the existence of this mosquito which is located at the center. Why? Because when you look at the global properties of the host galaxy, more specifically, if you look at the properties of the bulge of the galaxy, we find correlations. Of course, a correlation is not a causation, we know that. But in any case, we are doing what we can in astrophysics, and we find these correlations. We find that, for instance, the luminosity of the bulge correlates with the mass of the supermassive black hole. We know that the number of globular clusters in a galaxy correlates with the mass of the black hole. Why should the number of globular clusters correlate with the mass of something which is so small and far away? And even more tightly, we know that the mass of the black hole seems to correlate very well, in astrophysical terms, very well, with the velocity dispersion of stars around it. It's as if you are, I don't know, living in Barcelona, and let's say the Forbidden City in Beijing is affecting your speed in Barcelona. Why should that happen? We don't know, but we see these things, we see these correlations. Anyway, so in any case, if although we have these correlations, what we know is that no star which is rather far away, and in the case of the Milky Way, this rather far away means 3 parsecs away from the supermassive black hole, no star should be aware of the existence of this supermassive black hole. The potential well is dominated by the mass of the supermassive black hole, if you want. This is a way of defining this radius. So for us, this means that the conformal diagram on the right-hand side, so at these null surfaces, is going to be the same, because you are at infinity. You're not even 3 or 4 parsecs, you're at infinity. So the structure of space-time is going to be the same, okay? But as we get closer and closer and closer and closer to that supermassive black hole, interesting things are going to happen. And when we cross the event horizon, even more interesting things will happen. So I'm going to start drawing. Remember that this is just a very, very hand-wavy introduction to conformal diagrams, and there is a very solid mathematical apparatus behind all of this. Let me go to this share screen. Share screen. Yes. And here we go. Okay. Now I'm going to pick up this, and I'm going to start drawing things. So, as I was saying before, because we are very far away from the supermassive black hole, the right-hand side of this conformal diagram, or Penrose diagram, or Penrose-Carter, Carter-Penrose diagram, whatever you want to call it, is going to be the same, right? Because here we have this null infinity and null infinity surfaces. Okay. Now remember that there are some special points here. Yes, that's me. So anyway, there are special points here, and I'm going to draw them in say, I'm going to pick up, I don't know, whatever, red. This point here is a space like infinity. I'm going to mark it so that we remember it. There you go. So, space like infinity, okay? And that any causal thing must be contained within a cone of 45 degrees. I'm saying 45 degrees, but you know what I mean, right? So I'm talking about this, well, whatever, 45 degrees, okay? Well, now there is another special point here in this diagram, which is this one, also in red, probably, here. And that point is, as you can guess, time-like infinity. So, time-like infinity. Okay. So, when moving to Schwarzschild spacetime in vacuum, because this is what we're treating here, we do not have source terms, we don't have matter. Okay, we have just a zero on the right-hand side of the equations, and we assume perfect spherical symmetry. When you are far away from the black hole, you have the same kind of Penrose or the conformal diagram. Okay. So we have the usual flat space, if you want, a Minkowski space-time. So over here, everything is flat, okay? Now, I'm going to draw now lines corresponding to constant radii, which are going to look like this. Let me pick up, I don't know, for instance, I think this probably is a good option. Let me see. No, this is not a good option. Sorry, I don't still know my... This is not good. Okay, whatever. I'm going to take the usual thing and make it in another different color. For instance, I don't know, this one. So we have lines of constant radii. So this is a constant radii. For instance, a radii of, let's say, I don't know, 50 m. So r equals, no, let's say 10 m. And by the way, I am assuming here that c equals g equals 1, okay? And therefore, the radius has units of mass. This is just because I want to do this and because I can do it. So this is, let's say, I'm going to draw now different lines for different radii. So, of course, I have forgotten now the color, but my daughter claims that I am colorblind, and she's probably right. So that's that's 10 m. That's say 5 m. This is 3 m. This is 2.8 m. I don't know, 7 m. 2.4 m, say. Of course, this is not to scale. I hate that sentence, but I have to say that. This is 2.2 m. And so just to make sure, I'm going to add some labels, like say this is, I don't know, let's claim that this corresponds to 5m, and this is, I'm going to ignore from now the m thing. So this is 3, this is 2.8, this is 2.5, I don't know, 2.3, and something very interesting happens when we reach the value of exactly r equals 2m. Okay? What happens? We have a null surface, which is this one. I'm not going to show you it, I mean mathematically, show you it, but when you reach the 2m solution, you have exactly this surface here. Okay, so this is equals to 2. So here you have a null surface. Okay, and what is special about this null surface? Well, first of all, you can reach it in a finite time, and guess what? You can cross it. Let me make some room here. I'm going to delete these lines. Like this. So if you were, you know, an observer, and you would be traveling from, let me see, no, again, this is the wrong one. Oh my goodness, there are so many options here that I don't know which one should I use. Maybe this one. Yeah, this is fine. Okay, so let's take this one. So if you are an observer and you are starting your travel here, as long as your slope, remember, is not higher than 45 degrees, you can approach in your travel this surface in a finite proper time and cross it. There is nothing special about that surface. Okay? Now, you can cross it, but you cannot stay there. Why can't you stay in that surface? Why cannot you live here? Well, you cannot live here because you have a mass. And that's a null surface. Only photons can move there, which corresponds to the picture that photons are stuck at the event horizon of a black hole. Okay, so they are moving along that line, that surface here, but at a fixed radius. So the event horizon is a null surface. Now, let's make some room. I'm going to delete a couple of things, like for instance this, because it's a bit messy. I'm going to make this probably smaller because it's too large. Yes, like this. Yeah. So let me redraw that again. And it's really well. Okay. So let's take it and consider it. There you go. Very thick so that you can see it well. So what happens, what do you think that happens if you're a traveler traveling from here, again remember, oops, here, for some reason it is not working now. Okay, I'm going to take this one then, but smaller please. Oh, this is the opacity, okay. let me see. This is the size. Okay. So sorry about that, but anyway, this is the initial trajectory, and you're a traveler, and you're traveling towards that null surface, and you traverse it, you cross it. What happens when you cross that surface? You can understand now that as soon as you're inside, so as soon as you leave, so this is, if you want, this is out, and this is in. As soon as you are in, there is no way out. There is no way back. And why is that? That's because in order to get out of the event horizon, you would need to move horizontally with a slope larger than 45 degrees, and hence you would be moving faster than light. So once you cross that null surface, there is no way back to the external universe. Now, another question is, what happens to you? What happens to your trajectory? Okay, we have now learned that we cannot go back. But a different question is, what happens to your trajectory? What happens to your, by the way, this thing here is called a world line. What happens to your world line once you are within the black hole? I'm going to delete this now. Okay, so I have redrawn everything. We have on the top, we have this time-like infinity point. Time-like infinity point, yes. On the bottom, you have another time-like infinity point. Here, you have a space-like infinity point on the right. This surface on the bottom corresponds to a null infinity surface in the past, and we have the other corresponding one in the future. And we have explained that this is going to be a null surface. And I was asking you, what happens if you start your trip here and you cross, the event horizon at some point? Of course, it's supposed to be a continuous line. So what happens when you get inside? So, again, and as usual, and this is why I was insisting so much about those light cones, with a condition that your light cone continues to be, that your world line continues to be within a light cone, like this one, right? Oops. Well, you know what I mean. You're completely fine. So you actually do not realize about anything. You have your own proper time, and you're moving. Now, let's consider two travelers, or two observers. One of them will cross the event horizon, and the other one will continue the travel to the upper time-like infinity. Okay? So we have two travelers, say traveler A, which is the world line we just described, and we have traveler B, which I'm going to describe now. So this traveler B is going to start from the lower time-like infinity point to the upper time-like one, like this. Okay, and again with a proviso that this person is within, so the world line is within a light cone, things are fine. Now, because A and B are very good friends, A is a boy, say, and B is a girl, and I'm not going to draw a typical thing for girls. Actually, I'm going to draw the boy like this, because I want. This is the boy, A, and this is the girl, B. And the boy A, traveler A, it's not a gender, matters a lot. Traveler A is a very good friend of traveler B, and they want to keep in touch, so that from time to time, traveler A sends, an email which travels at the speed of light, or a signal which travels at the speed of light, to traveler B, like this, 45 degrees, right? So it must be parallel to this surface here. And this is not quite parallel, but anyway. And here, at this occasion, he asks B, how are you doing? Is everything fine with you? Are you getting sick? Here sends another email, and here he sends another email, and here he sends another email, etc., etc. But the question is, what happens when he crosses the event horizon? He's going to send the last message, yes, a wave, which is going to have a given wavelength a given wavelength, and it's going to take some time to get to the right traveler B. Okay, so if traveler A just, when I cannot draw it here because it's too small, but imagine that just 1 epsilon before crossing the event horizon, he sends a last email to his friend on the right. I don't know whether you can see that in the drawing, but the important thing to know is that because this wavelength of light is going to take an infinite amount of time to get from traveler A to traveler B, there will be a sudden cutoff in the signal, which is why we say, this is special relativity, that things get frozen as they come closer and closer and closer to the event horizon. What is actually happening is that because you have a given wavelength but an infinite amount of time, the signal will be infinitely stretched. So we're talking about an infinite redshift. Okay. Now only traveler B is going to need an infinite proper time. Proper time is the time that you're measuring, or in your own, you have each one of them has a clock, and this is the proper time of each of them. And because the bottom line is a time like infinity, and the upper point is a time like infinity in the future, traveler B is going to need an infinite amount of proper time to reach the time like upper point. The other lines will reach the null surface in a finite proper time, like a traveler A, even if they are massive, right? So, as you can see, this is not flat space-time anymore. Geometry starts to matter. This is Schwarzschild space-time. Contrary to flat space-time, in which the vertical line corresponded to r equals 0, here geometry starts to mess things up, and the null surface is located at r equals 2m. Now, because human beings are like this, you might wonder about one important thing here. I'm going to clean this now. So, this is what we have. We are constantly looking for patterns, right? And it is obvious to ask yourself what is going on here. What is this surface? right? And what would that surface mean? We understand what this surface here is. Here, we understand what this surface means. We understand what the point means. At least you trust me to understand what this means, because I have not proven anything yet. We understand what this point is. We understand what this point is. And we understand what this surface is. We need an infinite time to reach this. We need an infinite time to reach this point, to reach this point, and to reach this point. We do not need an infinite time to reach this surface here. But what about this size of the drawing? Now, that question must have been burning you from the beginning. And the answer is that the same way that things can reach the surface and cross it in a finite time, because time goes in that direction, things in the bottom left part of the diagram, the one with the shaded line, can cross that null surface, that's also a null surface, to get to us in this way. But, of course, we cannot get into there. And that once things have crossed into our space-time, they cannot go back, because for that you would have to move horizontally. With respect to that line, and you would be outside of this the usual slope of 45 degrees. So it's the same thing which happens to this observer falling onto the black hole. Okay. Now, because things get here inside and they never come back, we call this a black hole. You know that? Actually, they used to call them Schwarzschild throats, something like that in the past. And because on the other surface, exactly the contrary is happening, we call these surfaces, or not surfaces, sorry, this is not surface, sorry. We call these things white holes. Now, whether this is something real, physical, or a mathematical artifact, I actually don't know. And probably the worst thing about white holes is that they evaporate. They must, by definition, not by definition, because they're not defined, but it is obvious to understand that they must evaporate very quickly, without even requiring, Hawking radiation, because they are constantly outputting things into our space-time. Yeah. Now, one special remark that I would like to do is that there is nothing special related to the line joining the two time-like points in the diamonds. So these, surfaces of constant radius. This is a choice of coordinates, because the way we're drawing these diagrams is a tricky one. We are multiplying the metric by a conformal factor. We're compactifying the coordinates in a given specific way. So if we chose a different way of compactification, we probably would have imagined that this is a line corresponding to r equals 10. We could have, a different line corresponding to r equals 10, like this. It's just a choice of coordinates. The important, extremely important thing, and I will stress this about 10 to the 9 times, is that the only invariant thing in this diagram is the light cone and null surfaces. Let me make some room here. So here we go. We're going to get now, again, within the event horizon, and we're going to ask how do surfaces corresponding to constant radii look like. Remember that in the exterior of the black hole, these surfaces, of course this is not working, let me pick up another one, like for instance this one, were like this, right? This, like this, and then we put a stat, go like this, and exactly at r equals 2m, we had event horizon. Now, we want to understand, say that this is 10, 10.05, I don't know, 2.8, 2.3, and that's 2, okay? Now, we want to understand, we want to see how surfaces corresponding to, say, 1.m, 1.8m, 1.7, 1.6, 1.5 are going to look like. For that, we need to extend the space-time. And the answer is a bit puzzling. It looks like this. I'm going to, first of all, delete this and extend a little bit space-time. So here we are. So again, this is a surface of constant radius outside of the black hole. And this as well, but should end up there, sorry. And when you cross the r equals 2m, I have extended space-time, as you can see here. You can mathematically prove that lines of constant radii look like this. So this would be, I don't know, 1.8m, 1.7 m, etc. So horizontally, it is a space-like surface. What does this mean? This means that for a given slice, for a given fixed radius, for instance, I don't know, this one, we have the entire volume of the black hole at a given time. We don't have a fixed radius. We have the entire volume of space-time at exactly that moment. Now, as you can guess, because this is probably the most interesting part of the discussion, which probably will not happen today, as we get to r equals 0, things will go very messy. Here we are. So when we cross the event horizon, and we start to cross different surfaces of different constant radii. I don't know, for instance, this could be this one here could be r equals to 1.9, this one here, r equals 1.2, and this one here, r equals 1. When you get to r equals 0, bad things happen. The metric becomes singular. The metric becomes infinity there. And the curvature of the metric also becomes infinity. So, think about it. When you are inside of the black hole, there is no more global spherical symmetry. Okay? There is a different kind of symmetry. Since the metric depends only on r, on each of those surfaces, the metric is constant. This, speaking in a more earthly way, means that the interior of the black hole looks like an isotropic universe. It's like a cosmological universe. If you are sitting at one of these surfaces and you look around, it looks everywhere the same. If you change the slice, meaning the time is progressing, the light cone structure has not changed. Remember that this is invariant. Every time that this infalling observer crosses a surface of a given fixed radius, when he looks around, because it was a he, if you remember, this was observer A, what he sees is a constant universe, which is equal everywhere. Everything looks the same. And this is not the definition of spherical symmetry. It is isotropy. Now, there is a catch here, because this corresponds to fixed radii. But of course, you're not fixed. You cannot be fixed by definition. Okay? You're moving. And as you move, you will, suffer tether forces. And the closer and closer that you get to the last surface of r equals 0, it will be completely certain that you will have been destroyed. This is why when people draw a black hole and they say a black hole has an event horizon like this, and it has a singularity at the center, this is completely wrong and, well, nonsensical, because the singularity is not a where, the singularity is a when. Everything looks the same around you, remember. Because it is isotropic, there is no center. It's like asking yourself now, where is the center of the universe? Seems like we're going back to the Middle Ages. There is no center, and it is certainly not Earth. Of course, if you define the limits of the universe as the limits from which you can receive light today, there is some given size, etc. But in principle and theoretically, everything looks the same in all directions. There is no preferred place anywhere, and therefore there is no center. You cannot have the singularity at the center if you do not have a center. Again, the singularity is nowhere. The singularity is when, and it is in the future. It is the future boundary of the interior. And to speak clearly, when we say singularity, we only mean that we do not understand what happens there. If you want, this is very similar to discussing about the Big Bang. Yes, I have now figured out how to use the pause thing in the recording system, and this is very useful. So we were discussing about, describing a black hole with a circle and a point at the center. And I was explaining to you that this is nonsensical because there is no center. The singularity is going to be at the future. It is not in a place, in a location, which is why I dislike so much these illustrations that they do to describe the origin of the Big Bang. You have usually, you have this little point, and that point is expanding over time and is created the universe like a tube, and it's going in one direction. That's nonsensical because if you think about it, the Big Bang is the moment from which you can define, you have a space-time around you. But the message that those images are conveying is that you have a dot, and from that dot everything is expanding. But it's expanding where? Because when you look at the picture, you see a point lying on a surface, and that surface itself is also depicting space and time, so it doesn't make sense. So I hope that that has been clear now. The singularity is just the future boundary that you will hit in the future. And it takes the fraction of a second, in the case of a black hole, I think, for you to hit the surface at which r equals 0. Now, another point that I want to make is that there is another misconception about the interior of Schwarzschild black holes. Black holes, besides having isotropy, when you look at a black hole, at a Schwarzschild black hole from outside, it looks the same all the time. When we get inside of the black hole, this is not longer true. And in these surfaces that I was showing before of constant radii, which are actually slices of constant time, the metric is constant, but it differs from one surface to the next one. Having a constant metric is equivalent to having isotropy. It is the entire interior at a given time, because anything moving there has to cross that surface. The infalling observer, even if standing still, will necessarily see the geometry changing around because because he's moving. Remember, and whatever this observer does, they will have to progress crossing surfaces of constant radii, because he has to keep moving forward in time, upwards in the light cone. This means that the geometry is not stationary anymore. Mathematically, when you want to think in a rigorous way, sorry about that, you can prove this by elements of the Lie algebra. Sorry, I had to fetch the charger. So I was saying that you can prove this by using elements of the Lie algebra, okay, which allows you to study the symmetry of the problem, because this is an important thing, the symmetry of the problem. Inside of the black hole, there are no time-like killing vector fields, so that there is nothing that is stationary. You have a space-like killing vector field outside of the black hole, because over there space-time is symmetric. This is actually very well discussed in a book written actually by an astrophysicist, Straumann, in which he presents a rigorous derivation of what I'm talking about. You first find a solution. So remember how you have to proceed to find the solution of this problem. First, you have to find a solution for the metric outside of the black hole, which breaks at r equals 2m. From there on, you make an analytical extension, the Schwarzschild extension, to get inside of the event horizon. And there is a misconception about this, not technique, but a procedure, is that there could be alternatives, and then this would be, a mathematical artifact, because we're saying that, if you noticed, I will repeat this probably in the next video, but if you noticed, I say that when you cross the event horizon, if you looked at the diagram that was shown before, the radial coordinates transform into time coordinates. This is the analytical extension that I am talking about, the Schwarzschild extension to get inside of the black hole. And the nice thing is that there is a uniqueness theorem that proves this. So in spherical symmetry, there are no alternatives. So this is what it is. So again, if you want to look at the details, I recommend this book by Straumann, which is an astrophysicist who can deal very well with mathematics. And by the way, the appendices are a very good introduction to differential geometry. The second book, in which this is very well explained, of course, is the book by Hawking and Ellis, but it is harder to read. So, in any case, to sum up, when you fall into the event horizon, you are surrounded by an isotropic universe, and the geometry continuously changes around you to the point of squeezing you, if not in the end, at some point getting closer to the end. This means that the curvature keeps changing constantly, increasing as you progress in time. R equals 0, that strange thing that we had in red marked in the diagram, is the future boundary in space-time. It's not a place, it's a moment. There is no mass anywhere, by the way. And this is something that confused me a lot in the past. We are in vacuum solution. There is no source terms in the answer equations. But in the outside of the black hole, of course, it looks like we have a mass. In the interior, things are different. And at r equals 0, geometry ends. It is, if you want, like the Big Bang, but reverse. The end point is the end of time. It is as with the Big Bang. It did not happen here or there, but at a given time. And it happened everywhere, because the universe is isotropic, and the interior of a black hole is the same. It is important to note that this is something that I did not explain before, that each of the surfaces that I was drawing with a constant radius at the interior of the black hole have an infinite volume. But again, to go back to what I was describing before, I found this extremely perturbing, if you want, because for me, and I hope for you, curvature is linked to mass, and mass is linked to curvature. So think about it. How can you have curvature if you are in the vacuum solution? There is no mass anywhere. I think I'm going to wait until the next video and just leave this question here for you to think about. How can you have mass in an intuitive way, because we're not doing mathematics here, this is just a hand-wavy introduction to this subject, but you can intuitively understand how you can have curvature without having mass. And it is, by the way, very closely related to the drawing that I did when I had a null infinity surface here, the other one here, the event horizon of the black hole over there, and then in dashed lines I was drawing you the event horizon of the white hole. There is a connection between the two things. Maybe you want to think about it and give a try before the next video comes out, if it ever comes out. If you want to ask me any question, again, you can send me an email, and my email address is amaro@riseup.net. Thank you, and talk to you.